Okay, today's lesson has to do with something called molecular geometry classification. So this is going to prepare you guys for into next week when we really take a look at the geometry, the actual shapes that these molecules take on in three-dimensional space. So when we are drawing out these Lewis structures of these molecules, we're really only seeing a two-dimensional view, okay? So that is the X and the Y, okay? So this screen, as well as like the whiteboard in my classroom or a sheet of paper, that's only giving you two dimensions, all right? So next week we'll actually see how these spread out three-dimensionally and how we can actually depict those on a two-dimensional screen or a piece of paper, okay? So these are two molecules that we've already looked at over the past week. These were on one of your practice sets that you've recently completed. So in each of these, okay, molecules, so right here, here's your formula. This is CH4, which is methane or carbon tetrahydride. Methane's just its more common name. So you can see carbon's your central atom, and then you've got your four outer atoms. Now here, this is carbon that has two chlorines and two bromine ions attached to it. So carbon is your central atom, and then you've got these outer atoms. Now, notice that the lone pairs I left off, okay? The reason why I left the lone pairs off of the outer atoms is not because they're not important, because they're obviously important to making sure that your structure is drawn properly, but they're not important in terms of geometry classifications, okay? So first thing is, let's talk about this letter system that we're going to be using to classify molecules. So the letter A stands for a central atom. The letter B stands for an outer atom, and the letter E will stand for a lone pair. So these two molecules have the same geometry. They have the same geometric classification. They are what we call AB4 molecules, okay? So this is an AB4 molecule. This is an AB4 molecule because A, as I said, represents the central atom. B represents an outer atom. So each one of these have four outer atoms, all right? So these are what we call an AB4 molecule, okay? And AB4s actually take on what is known as a tetrahedral shape, which is something, like I said, when we get into the classifications next week, then you'll see that a little bit more, all right? So AB4 is just one of your classifications. There's a total of 6 that you have to learn for this class. Okay, so these next two, carbon dioxide and cyanic acid, are also in the same geometric classification as each other. They are not AB4s. Instead, they actually only have a central atom. Now, there's double bonds on each side right here, which allows this carbon to be stable. All right, and again, would usually be lone pairs over here on the oxygens, but those are being omitted because they do not affect the classifications. We're only looking at what is around the central atom, okay? So you've got a central atom, and then you've got two outer atoms. There's no lone pairs around the central atom. So this is what is known as an AB2 molecule. This is also an AB2 molecule, okay? In both cases, you have one central atom, okay? You've got an outer atom on both sides, but you have no lone pairs. So this is what we call an AB2. And here is the next classification. So again, we're focusing on that central atom. So you look at your central atom. This is carbon, and you can see it has 2, 4, 6, 8. There's the shared regions that make it stable, 8 valence electrons. So you've got a central atom, and then you've got 1, 2, 3 outer atoms, no lone pairs. So yep, if you're catching on to this, that means its geometric classification is going to be AB3. That's one central atom. Here's your A, and then you've got 3 outer atoms. Those are your B's, okay? Okay, so I put the last 3 classifications on here together so we can kind of look at their differences and then what they have in common as well. So what's different from these classifications than the last 3 that's been mentioned is that there are lone pairs around the central atom. So notice, once again, I purposely have left off the lone pairs around the outer atoms because those aren't necessary. I want you guys to understand what we're looking at is that center atom and what is surrounding it, because the central atom is like the glue in the molecule, and it actually is what is going to dictate all of your geometry, how these items that are surrounding it are going to float and rotate and position themselves, okay? So right here, this phosphorus trichloride, you've got a central atom, you've got 3 outer atoms, and then you have 1 lone pair. So this is what is known as an A, B, 3, E molecule. It has 1 central atom, 3 outer atoms, and 1 lone pair, okay? So this right here is a lone pair. I understand it's 2 electrons, but that's 1 pair, all right? So a lone pair, again, remember, is not a shared pair. It is a pair of electrons that are not connected to another atom, all right? Now, over here with the H2S, all right, you have sulfur is your central atom. It's got 2 outer atoms, and then it has 2 lone pairs. So where you see a shared pair, that's going to count as a B, right? So this is a B, this is a B, right? This is an E, this is an E, all right? And of course, your S is your central atom. So this is what's known as an A, B, 2, E, 2 molecule, all right? So that means it has a central atom, 2 outer atoms, and then 2 lone pairs. All right, so here's the last one. You have, now it does not matter that this is a double bond. That doesn't affect the classification, all right? Now it means that this bond is stronger than this bond to this oxygen because it's a double bond instead of a single bond, but it doesn't affect the classification of the geometry. So you've got your central atom, A, you've got an outer atom here, you've got an outer atom here, that's A, B2, and then you've got only 1 lone pair. However, the central atom is stable, right? 2, 4, 6, 8, it's stable. All right, so this would be A, B, 2, E. All right, so you don't have to put a 1, just as with in most cases, there's an understood 1, right, for the letters that classify the lone pair and the central atom in these, right? So that's understood. All right, so these are going to be your different classifications of geometry when lone pairs surround the central atom, okay? All right, so now we can take a look at all of these on the same screen. You've got 1, 2, 3, 4, 5, 6 different geometric classifications that we will cover in this class. There are actually many more, but these are the most common and the major types, all right? So you've got your AB4, central atom. Now, and then what I've done is I've drawn the ball and stick models. So I'm actually displaying their geometries, like the actual shapes that they will take as best as I can on a 2-dimensional screen. So this right here, we'll talk about this. This is an AB4 molecule, and it's actually called a tetrahedral. This is a what we call a trigonal planar. Again, I'm not going to get into all the geometries right now. We just need to be able to, you guys have to be able to classify, okay? So you got a central atom and 3 outers. Here, you've got a central atom and 2 outers. Now, notice how I'm not representing if there's a double bond present or a triple bond. We don't represent these in the ball and stick models. It's just, hey, here's the central atom, here's our 2 outers, right? Now, there's lone pairs present. You can see I have this in the orange down here. And in AB2E2, you've got a central atom, and then you've got 2 outers, and then you've got 2 lone pairs. Here, you've got a central atom, 3 outer atoms, and then only 1 lone pair. And here, in this AB2E, it's a central atom, 2 outer atoms, and then 1 lone pair. So we're going to take a look at just a couple so that you guys know what the expectations are going to be for how to classify over the next day or so. So we'll do that, and then we'll be done. We'll wrap this up. Okay, so here we have the molecule nitrogen trihydride. And so I wanted to use this one because here's the deal. Students will take this question, and it's like, what's the geometric classification for NH3? And if you don't know any better, and if you don't actually learn how to do this properly, a lot of students will go right here, They're like, this is an AB3. This is an AB3 molecule. It's got a central atom and there's the 3 outer atoms. Now that's actually wrong. So the only way that you can actually determine the classification is actually to draw out the Lewis structure. So we're going to draw this out and see that it's actually not AB3. Okay, so when we take the molecule and we break down its formula and get a valence electron count, we will see that there is going to be a total of 8 valence electrons in this molecule. Nitrogen is our central atom. Hydrogen, those are our outer atoms. And we're just going to place them to the left, right, and below. We are going to link up the central atoms to the outer atoms with a shared pair. Once we do this, we check for stability on those outer atoms, and sure enough, they are all stable. And so we've got 2, 4, 6 electrons. We've got 2 more we can draw, and that's good because we need 2 more to ensure that our central atom, nitrogen, is now stable. All right, so we're going to clean this up so that we've got our shared pairs. The one where we have electrons between atoms, we want to draw that bond line. So what we see is that this molecule is actually an AB3E. You can see that this is an AB3 molecule that actually has 3 outer atoms and 1 lone pair. So technically, this is what the geometry would look like. All right, so, and you guys will learn how to do this later next week, but you would actually draw it so that it is actually representing what is known as a trigonal pyramidal geometry. Again, you don't have to know the geometry just yet, but this is an AB3. Central atom, 3 outers, and 1 lone pair, and it takes drawing it out to actually determine correctly what the classification is. Okay, so we're going to look at just one more, and this time we are looking for this polyatomic ions classification. What's the classification for this carbonate ion? So CO3 with a 2 negative charge. Again, let's not jump to going, oh, this is an AB3. We need to determine that. So we're going to break down this formula and count up our valence electrons. 4 for carbon, 6 for the oxygens. That's going to be 22 plus the additional 2 valence electrons, right? Because there's a charge there, all right, on the polyatomic ion. So that's 24 valence electrons total. All right, so carbon's going to be your central atom. I'm going to take my oxygens and put them on the outside. I'm going to now link my central atoms up, or my outer atoms up to my central atom. Once I do that, I want to make my outer atoms stable. So I'm going to go ahead and give them a full octet because we always take care of these outer atoms before we take care of the central atom when drawing a Lewis structure. So we've got 8 here, we've got another 8 here, and then we've got 8 here. So that's already 24. 8 plus 8 plus 8. 8 times 3 is 24. We've already used all 24 of our valence electrons. So this is where we use the technique that was learned this past week, which is to lone pair shift. So what we're going to do is we're going to just choose, because right now we have already drawn all 24 valence electrons and the central atom is not stable. It needs 2 more, but we can't draw 2 more electrons right here because we don't have any more left to draw. So we're just going to pick one of these oxygens to remove a lone pair, and then we're going to shift it to between right here. So now you can see that the the oxygen is still stable with 8, and then of course these were untouched, and now the central atom is stable with 8. Now everywhere that there is a shared pair, that is, there are electrons between 2 atoms, 2 elements, all right, we are going to draw our bond lines. That is, we are going to show that shared. So we're going to show the bond line, all right? And then right here, this is a double bond, so we're going to have 2 right here, all right? So now, we can now look at our geometry. Now, so let's look at the central atom. We've got a central atom, we've got 3 outer atoms, we have no lone pairs around the central atom. Now, granted, we've got these out here, okay, and that's why earlier I was showing you guys that we can just kind of ignore these, right? We had to draw them in order to come up with the correct molecule structure, but we don't need it to classify our geometry. So now we're kind of done with those and don't really need them anymore. So I'm going to clear them off so I can just show you guys, here's your central atom. You've got 3 outer atoms. There are no lone pairs. Everything is shared, right? So you've got an AB3. So this is an AB3 molecule. So you can see how each one, the one we did NH3 and CO3, 2 negative, ended up being 2 different molecule classifications, all right? And it took us having to draw out its actual molecular Lewis structure, all right? So this is what this would actually look like. It's an AB3 molecule, all right? So the key to these is not, the difficulty does not lie in actually classifying them. It's just you're going to have to take the time to actually draw out your Lewis structures. So we're actually building upon the drawing Lewis structure skill to actually now classify its geometry as either being AB4, AB3, AB2, AB2E2, an AB2E, or an AB2, AB3E, or an AB2E.